Okay, this is Chapter 10, Introduction to Simulation Modeling. Now, in this chapter, we're going to be looking at models that do not use solver. So far, all the chapters that we have looked at, except for Chapter 2, we used solver with simplex LP, except for the last chapter, which is Chapter 7, where we used solver with GRG nonlinear. This chapter, we're going to be looking at probabilistic input values, and we're going to be using an approach called Monte Carlo simulation, and it does not require solver. So we will not be using solver in this chapter. So what is simulation modeling? Simulation modeling is a computer model that tries to imitate the real life situation. So we'll have some input in a regular model like what we saw in Chapter 2. So we have some input values, some decision variables, like input value could be your demand, decision variable could be the quantity that we're going to order and keep in stock, okay? And then what the outcome will be, which will be like how much profit we'll be making. Now, if the input values are not deterministic, like if the demand is not 500 or 700, it's not a fixed value, but it is a value that fluctuates, or it is uncertain what the value is, but it can be anywhere between 400 to 600 with some sort of probability distribution. So when you allow for that random fluctuations in values of the input, and that would imitate the reality much better than simply saying the demand value would be 500 and not anything different. So when we allow the input values to vary according to some probability distribution, then we are introducing simulation analysis into this. So we will simulate what the demand would be, and based on that, or other input variables, and based on that figure out what the output variables of interest will be like, and we analyze these output results along with the input to arrive at a decision. So in simulation, we try to imitate what the real life situation will be. In real life, what would be the fluctuations that you're likely to see. So you take that model, set it up, and then repeat the model. Okay, like for example, if it is daily sales, you repeat the analysis for say 100 days or 200 days, and then look at the output values and analyze the output values. What kind of distribution we have for the output, like the profit, what is the minimum profit we will make, what is the maximum profit we'll make, and so on. So this kind of analysis, or setting up a simulation model that includes random input values, okay, set up the model and repeat the model for n number of time periods. So that is Monte Carlo simulation. So here is a graphical representation of the two different models. A deterministic model where we do not incorporate any probability for the input values. So we have your best guess for our input, and then we have the model, and we have the output that comes from the model. So we probably use the average value for the input. Like if you're talking about demand, we take the average daily demand and use that average in our analysis. And when we do that, we get one particular output. But in reality, what the actual values of the input is going to be very different from the average value. But we ignore all of those variations, so we end up with unrealistic output values, and that's called the flaw of averages. Now instead, if you use probability distributions for the input values and use simulation modeling, and we repeat the analysis for certain number of replications, as it is called, say 100 replications or 200, even 1,000 replications, then we get a realistic range of output values that we can analyze for making proper decisions. So introducing probability into the input values is what we do in simulation modeling. Okay, now what kind of probability distributions can we use for the input variables? Okay, and we can look at them in several different ways. You can have a probability distribution that is either discrete or continuous. Or it can be symmetric or skewed. It can be bounded or unbounded. Non-negative versus unrestricted. So let's look at what these are, some examples. So this is a discrete probability distribution where we have some specific possible values, and for each specific value we have a probability. So for example, if the demand is going to be either 100, 200, 300, 400 or 500, and that's it. And for each value we have a probability, and the probability is sum to 1. So that is a discrete probability distribution, finite number of possible values. As opposed to a continuous distribution is one in which there is a minimum value and a maximum value and any value in between, not some specific ones, but within a range, any possible value or any value on the continuum is a possible value. Then what we have is a continuous distribution. So when you look at this shape, you can see that this looks like a normal distribution, and normal distribution is a continuous distribution. So that is discrete versus continuous. Now symmetric versus skewed. So this here is a normal distribution. It is symmetric because around the center the left side and the right side are mirror images, and so it is a symmetric distribution as opposed to skewed distribution. So here we have a distribution that is skewed to the right. So which means there are large values are possible, even though the probabilities are small, then extremely large values are possible. And this is a distribution that is skewed to the left, and this means that on the higher side there is probably a kind of a bound, but on the lower side really small values are possible, even though the probability of such values are really small. So there are two different types of skewed. So we saw symmetric in the previous slide, and these are two possible examples for skewed distribution. Now bounded and unbounded, a bounded distribution is one which has a possible minimum value and a possible maximum value. So any value between say 100 and 500, any value. Okay, so that is a bounded distribution. But if any one of those two bounds is not there, so there is a minimum bound, but there is no maximum bound. Any value on the higher side is permitted, or the other way around. There is a maximum bound, but there is no minimum bound. Or probably there is no minimum or maximum bound. In either direction it is unbounded. So those probability distributions are unbounded. Technically speaking, normal distribution is an unbounded distribution because there is no left side limit, theoretically speaking, and there is no right side limit, again theoretically speaking. So theoretically, normal distribution is an unbounded distribution in both directions. The exponential distribution is one which is on the positive side. The minimum is bounded by 0, and the maximum value can be any value. So that is an example of a distribution that has a minimum bound, but there is no maximum bound. Non-negative versus unrestricted. So non-negative would be an exponential distribution where you cannot have a value that is negative. Unrestricted is, of course, there is no restriction. The common probability distributions we are likely to see on the discrete side, you can have Poisson distribution, or you can have uniform distribution, you can have binomial distributions. Uniform distribution can be both discrete as well as continuous. If it is a uniform distribution with specific values with equal probabilities, like 100 to 500, each with the exact same probability. 100, 200, 300, 400, 500, each with the probability of 1/6, 1/6, 1/6. Then we have a discrete uniform distribution. Or if you have a uniform distribution anywhere between 100 and 500, any possible value. So that will be a continuous uniform distribution. Other examples are normal distribution, exponential distribution, beta, and triangular distributions. Triangular distribution would be one which will be like there is a minimum value, there is a peak value, and there is a maximum value. So we'll be looking at these probability distributions for the input variables in a model. We'll look at these in a little bit. Now, simulation and the flaw of averages, and as I mentioned earlier, in a deterministic model, we use the average value for the input variables. The average value of the input variable rarely would occur because there will always be some fluctuations around the mean, and therefore simulation results takes into where simulation modeling will take into account all possible values for the input variables according to some defined probability distribution. And we'll be using two approaches for the Monte Carlo simulation. First, we'll be using built-in functions in Excel itself without using any add-on product. So we'll look at those examples, and then we will be using a particular add-on software for Excel called @risk. @risk is a product made by Palisades Corporation, and it is part of the decision analysis toolkit, and it allows for many more possible probability distributions than what is available by default in Excel. So a lot more variety, and also it makes replications of simulation a lot more easier, and the output possibility when you have the Excel the simulation model outputs, and you can, if you use @risk, then there are a lot of possibilities of presenting that output in more useful ways. Okay. @risk is only one product. There is another one called Crystal Ball that does exactly the same thing like @risk, and there are probably other software packages available for doing Monte Carlo simulation as well. So from the next video onwards, we're going to look at specific examples. First three of them would be using only the Excel functionality, and then the rest of them would be using @risk.